Welcome to Process Control Design and Practice. My name is Tom Meadowcroft. In this video, we will learn about control system architecture. In the text and in my classroom, I give a history of automation from the Industrial Revolution to today, but I'm going to leave that out in the interest of time. I'll summarize by saying that we've gone from mechanical through pneumatic, electrical, electronic, and now software configurable control systems to get where we are today. A modern control system for a process, whether it is called a distributed control system or a connected series of programmable logic controllers, shares a lot of functionality with how the internet works. Your control system is a system of networked computers, so we need to understand the basics of how computers and computer networks work to understand the capabilities and limitations of your control system. Not every system is identical, but this is the basic structure that is most commonly found today. The computers that make up a control system are connected by cable and communicate using the industrial Ethernet protocol, which is a communication standard for network computers, very much like the various protocols that define how the internet works. Every device has an Ethernet switch, just like the internet, with an address that allows them all to talk to each other. There are controllers, which are the super fast workhorse engines that talk to the sensors, pumps, and valves, run feedback loops, digital logic, and sequences. There are operator and engineering stations, generally PCs running software on Windows, that allow operators to operate and engineers to configure. And there are servers to handle data storage, a batch recipe manager, and various system maintenance functions. Each controller, often on its own local Ethernet loop to manage traffic, talks to one or more racks full of input-output or I/O cards, and each card communicates with 4, 8, 16, or 32 devices like sensors, valves, and pumps. So let's cover some basics. Computers store data in transistors or bits that are on or off, true or false, 1 or 0, which is Boolean or base 2. 8 of these bits make a byte, which can range in decimal or base 10 from 0 to 255. The Internet Protocol IPv4 gives every device a 4-byte address. Although the Internet has moved to 6-byte addresses for more capacity, the little internet, which is your plant's control system, will do just fine with IPv4 addresses. Now, 2 bytes gives us 256 times 256 integers, which is 0 to 65,535, or more often, negative 32,768 to 32,767 when we use the first bit as a sign. This is called a double precision integer, which is important to us. Most of our input-output devices that we receive and send data to and from will communicate using double precision integers because that gives us 4 significant digits of precision, which is as much as any of our sensors or devices can use. While high-speed communication to I/O devices uses these integers, a controller will also use real number variables, strings, and binary variables internally. See the text for more detail. When a pressure sensor measures a pressure from 0 to 5 bar in the field, its transmitter sends an electrical current down a wire ranging from 4 to 20 milliamps to an input card. That analog current is translated into a double precision integer in the card. That 2-byte integer is sent to the controller, which translates the double precision integer from 0 to 65,535 into a real number in an analog input point that knows that 0 to 65,535 corresponds to 0 to 5 bar because we configured it that way. In the same way, but in reverse, the controller can tell an analog output card to send a 0 to 100% signal to a control valve, or tell a digital output card to tell an actuated block valve to open or shut. That's the traditional communications path with analog electrical signals. Today, more digital information may be piggybacked onto those basic signals. See the text. We started talking about input-output or I/O cards. There are several different types. Some are input cards, some are output cards. Some have both input and output points. Each card is either for analog double precision integer signals or digital true-false signals. There are special cards for RTDs and thermocouples. Cards have between 4 and 32 points, each of which talk to one device. I/O cards fit into slots in an I/O rack. A rack generally has 4 to 12 slots, one of which is used for the Ethernet switch that has an IPv4 address and sends and receives thousands of signals per second via the Ethernet ring to its controller. The rest of the slots will have a variety of I/O cards which will enable one rack to talk to several hundred devices. A rack sits in an I/O cabinet to protect it. A rack is placed as close as possible to its devices in the field, as either 2 or 4 wires has to go to each device from the rack. Only 2 Ethernet cables go from the rack to the rest of the loop that includes the controller, so racks and controllers can be a larger distance apart. Controllers are generally kept somewhere safe, cleaned, and air-conditioned. Wireless communications with devices is possible but tricky. See the text. When signals arrive or leave a controller for a rack, they carry an address which specifies rack slot and point number. Part of the controller's job is to translate a double precision integer from the analog input card at rack 14 slot 5.11 into a pressure reading for PT-R54 with units of 0 to 5 bar absolute, or a command to open SV-R54B into a true or 1 signal to the digital output card at rack 14 slot 7.27, which is wired to that R54B valve in the field. There's a lot of electronic bookkeeping that goes on in a control system with hundreds or thousands of points. We've now mapped how analog and digital measurements and commands move from sensors to real or Boolean numbers attached to tag names in the controller, and in the opposite direction for outputs. What is happening in the controller, the workhorse of the system? The answer is almost everything, other than operator graphics and data storage. Controllers first have to process all of those I/O signals, scaling and aliasing to tag names as needed. Feedback loops need to be iterated several times a second. Lists of digital logic, that is, interlocks and permissives, must also be processed, as well as sequential logic in phases for batch plants or production modes for continuous ones. Controllers are very fast computers processing many lists of tasks one at a time. We need all of these tasks to be performed 3 to 4 times a second, or performance will be noticeably slow, so once every 250 to 400 milliseconds. If a controller does not finish its list before it is time to start again, it will leave the last items on the list unaddressed. So it is vital to never load a controller more than about 70% of its capacity under normal operation, because we do not want to run out of capacity in a crisis. Depending on the controller and the complexity of the task to run, 200 to 500 I/O points on a controller is a comfortable loading, which will determine the number of controllers needed for a facility. On the main Ethernet loop, controllers exchange data and messages to each other as needed. Data is sent to operator and engineering workstations, which are generally just desktop PCs running workstation software that generates the graphical user interface. Whereas data and logic on the controllers and I/O need to update several times a second to process safety interlocks or stop charges accurately, data on the main loop need only update at human speeds. In a control room, you're seeing a virtual echo of the plant and controllers working with a 1 to 2 second delay. Data is stored in a historian, and a batch recipe manager stops and starts phases, all from a central server that doesn't need lightning fast communication to do its job. Control systems are an expensive but necessary part of any modern process plant, essential for productivity, safety, and quality. Installation costs of $3,000 to $5,000 a point are typical, with a third of that cost going to system hardware, a third spent on installation, mostly labor, and a third spent on software. Process control will often cost 20 to 30% of many complex projects. Network computers, which 30 years ago were uncommon outside of the military and automated process plants, are now everywhere because of the internet. This made Ethernet switching and communications gear cheaper, so modern control system structure now resembles that of the internet to use those cheaper components. Any project needs enough controllers, racks, I/O cards, and workstations to allow the system you design to work smoothly. A working knowledge of control system architecture will help a chemical engineer understand this important center of cost and complexity in any major project. Look for a full text, exercises, and more videos at chemicalengineeringpractice.org. I'm Tom Meadowcroft. I hope to see you again soon.